Hello everybody, I hope you are doing well. In this presentation, I'd like to give you some information about the 3 papers in the field of UAV networks and software-defined networking, or SDN. The first one is SwarmControl, an automated distributed control framework for self-optimizing drone network. FANETs or UAV networks consist of thousands of mobile connected drones. So providing an optimal control strategies for UAV networks is still an open issue because there are inflexible wireless interfaces in commercially available UAVs that are sensitive to changing topologies. So functionalities such as point-to-point communication, network formation are impaired by unstable channel conditions. Traditional network control scheme often have an assumption that network operator is aware of real-time network state information and is aware of low-level network infrastructure details, but the assumption often does not hold on distributed aerial networks. And controlling the network behavior and flight operation is in a dynamic environment requires a deep understanding of the interaction between the motion and network functionalities at all layers of the protocol stack. So what's the objective? The objective is designing a new software-defined framework that they call it SwarmControl in this paper to control the behavior of distributed UAV networks. The SwarmControl structure consists of 2 main parts: control framework. The control framework consists of control interface, distributed algorithm generation, network control, problem constructions, and this part includes some other categories. And the second section is drone programmable protocol stack, or drone PPS, which includes 3 planes that I'll explain you in the next slides. The control framework, its first part was control interface. The interaction with the network operator is implemented through a control interface, which consists of a set of high-level APIs and protocol libraries. The control interface provides the network operator with an abstraction of the UAV network, and it hides the low-layer network functionalities and information like the number of UAVs, their computing capabilities, battery levels, and it also enables the network operator to have the desired network behavior, and to determine which layers of protocol stack to involve in the optimization problem process, and some other possibilities. The second part of the control framework is network control problem construction, or NPC. The NPC construction is the first step towards distributed control of a UAV network. Once the optimization problem defined, SwarmControl converts the network operator's directives and requirements into a set of mathematical expressions, and the resulting NCP is a centralized representation of a high-level network behavior defined by the network operator through the control interface, and it spans both the networking and flight control domains, involving multiple nodes and all layers of protocol stack. The third part of the control framework is distributed solution algorithms generation. The resulting NCP cannot be solved at a central controller that has no access to time-varying network state information. The overhead and delay to retrieve such information in such scenario might lead to insufficient and suboptimal network solutions. So, SwarmControl employs decomposition theories to loosen the coupling among optimization variables, and generate a separate variables versions of the NCP to be decomposed. This procedure consists of 3 fundamental steps. The first one is optimization variables and parameter detection. SwarmControl first parses the objective function and then constraints of the NCP, and detects the optimization variables and parameters involved in the optimization problem. In doing so, it assigns variables to protocol layer functionalities to be optimized, and some parameters are considered as constant. The second one is problem decomposition. The objective of the decomposition is to loosen the coupling between optimization variables of the NCP. To do so, SwarmControl shows the network and network layers using a layered coupling graph. That in this graph, the vertex the vertex are optimization variables of the NCP and are associated to a specific layer and a specific node. The edges are coupling relationships between variables of the problem. The last one is distributed algorithm generation, which is the final step. For each of the decomposed subproblems, an algorithm is automatically generated to calculate the numerical solutions associated with a given network control variable. Each algorithm is then transferred into an executable script that some variables appeared as keywords, and these keywords can stored as a dedicated library installed at all network nodes and so forth. The second part was drone programmable protocol stack, or drone PPS, which is installed at each UAV to solve the numerical solution algorithm received from control framework in a distributed fashion. It includes 3 planes. Decision plane. This plane contains a protocol repository with the software implementations of different network protocols and motion strategies, together with the mathematical solvers to run dispatch scripts. The decision plane is responsible for running the distributed optimization algorithms based on the latest network state and motion information as an input parameter, and such information is retrieved from the register plane, which is also employed to store the computed numerical solution. The second one is the data plane, which is responsible for implementing the computed optimal solutions by reconfiguring the network and flight control operating parameters. To do so, the data plane implements a fully programmable protocol stack that spans all the network and motion layers. The protocol stack provides the building blocks and primitives necessary to prototype complex cross-layer and cross-domain network protocols and motion strategies that allows complete control of the network, sensing motion parameters, and at all layers of the protocol stack. And the register plane acts as a middleware that allows a decision plane to retrieve fresh data from the data plane and making computed optimal solutions available to the data planes through a set of dedicated lookup tables. The second paper is a SkyCore, moving core to the edge for untethered and reliable UAV-based LTE networks. Mobile operators are able to deploy LTE base stations on UAVs to provide connectivity for emergency scenarios. The typical LTE network, requires 2 main components. The first one is a radio access network that consists of multiple base stations and provide wireless connectivity to clients. and the second one is a high-speed wired core network of gateways, or evolved packet core, that called APC, which sits behind the radio access network, and it is responsible for all mobility management and control functions and routing user traffic to or from the internet. There are some fundamental limitations and challenges when we want to deploy an APC on the ground or in the cloud. The first one is resource challenge environment, and the second one is mobility management. What others do in this paper, they try to redesign of APC, and they called it edge APC architecture to suit the UAV environment. They aim to push all entire APC functionality to the extreme edge of the core network, and they call the infrastructure SkyCore, and it includes two key pillars. The first one is a complete software refactoring of the APC, and the second one is a new inter-APC communication interface that I'll explain you in the next slides. The APC structure consists of data plane and control plane. The data plane enforces operator policies on data traffic to or from the user equipment, while control plane provides key control and management functions such as access control, mobility, security management. E-node BSs are connected to the serving gateways, and the serving gateway is connected to the packet network through data packet gateways, and the data packet gateways enforce most of the data plane policies and may connect to the core to other IP network services. The EPC actually forwards each UE's data traffic between E-node B and data packet gateways using a separate GTPU GPRS tunneling protocol. The mobility management entity MME is responsible for access control, security, and mobility functions in conjunction with the home subscriber server or HSS database. Okay, as I've already mentioned, SkyCore includes software refactoring of the APC functionality and efficient inter-APC communication that I'll explain you. The software refactoring of APC contains two parts: minimalistic SkyCore agent architecture and a SkyCore pre-computed policy data store. The minimalistic SkyCore agent architecture includes some steps. The first one is decoupling the APC control and data plane pipelines. One of the main reasons behind the high complexity of APC is its node performing mixed control and data plane functions. So to make the APC functionality suitable for UAVs, we need first decouple the APC control and data planes. Then they categorize the APC control nodes based on their high-level functionality. There are three types of nodes: the serving gateways, the packet data network gateways, the mobility management entity, the home subscriber servers, HSS, that I've already mentioned. And others extract the internal functions in serving gateways and packet data network gateways and refactor them into a single SDN application on top of the controller. The mobility management entity is also transferred into LTE mobility application. The next one, they eliminated the HSS and PCRF. That the PCRF often access a logical database and dynamically generates different quality of services for users. They completely eliminate these two nodes, HSS and PCRF, from their agents and show that dynamic policy generation can be carefully replaced with pre-computed in-memory policy data store. And the next one is adding, UAV control application and UAV specific SDN applications to the core. The last one, SkyCore eliminates the need for hierarchical gateways on each UAV. To further make agents compact. Others refactor the server gateways and data packet gateways functionality into a single software suite. And, they use a separate match action table in this software suite. And the second one is a SkyCore pre-computed policy data. In a SkyCore pre-computing policy data store, we have a pre-computation of security policies. Network access security in LTE network relies on the shared user-specific key that is stored in HSS and user SIM cards. The LTE security processes assume that cloned users and spoofed networks do not know the correct value of the key. From the key, the HSS dynamically computes an authentication vector and encryption vector as part of a larger LTE attached process when users switch on or enter an area with LTE coverage. It also includes pre-computation of service policies. In LTE networks, the PCRF feeds the data packet gateways and service gateways with real-time quality of service rules. For example, there are some rules for quality of service, priority, charging. Some of them are static, and there are these rules in pre-computation of service policies. And we have also efficient inter-EPC communication. Every UAV runs its own EPC agent. SkyCore enables a new control data interface that allows agents on different UAVs to proactively synchronize the state of the UAVs. The segment-based overlays equipped with global source routing includes tunneling. Others interconnect each pair of the neighboring agents using a tunnel different with a label. And the routing, in a SkyCore, one of the UAVs is selected to double up as a master agent that is responsible for global route computation. They also employ a tunnel between every pair of UAV agents that will require updates to a large fraction of the tunnels, even when only a small number of UAVs move. But most of the SkyCore tunnel segments do not change in such scenarios, as they are designed to carry aggregate traffic only between the nearby pairs of UAVs. And we have also proactive stateless mobility support, which includes idle mode mobility or paging and active mode mobility hands off. The third paper is an SDN framework for UAV backbone network towards knowledge-centric networking. The management of UAV network is a tough task because massive information exists in UAV networks, like flight and control information, the sensing information, protocol stack information in UAV network, and also there are obtained information from ground terminals. And the second one is, the wireless links and network topologies are changing in UAV networks because of the UAV motion. So the question is how to manage the large amount of information in UAV networks. In this paper, to solve this, they proposed a monitoring platform in SDN controller, and then they proposed a load balancing algorithm to achieve a full utilization of UAV resources that I'll show you in next slides. As you can see here, the communication objects in SDN-based network are UAVs, user equipment, control links, data links, And there are also two types of controller: the UAV controller that manages information including flight control, physical location, battery storage, and the SDN control that can be either ground-based or sky-based and manage the information about UAV's network and interact with the UAV controller. The purpose, the authors proposed a monitoring platform in SDN controller to obtain and process the network knowledge, which includes monitor display, flow management, link management, and strategies. The monitor display shows system status and provides GUI to users. Flow management module is used to manage flow, including creating a dictionary for each flow, deleting flow, and configuring parameters for each flow. And flow indicates a group of packets which are transmitted from one network endpoint to another in SDN. And then link management module manage the link load considering the update from UAV and other modules. Algorithm and protocols are developed in a strategies module depending on different application demands. The other modules in the controller are responsible for information gathering and calculating. For example, packet loss rate calculation module collects the value of counters from the first and last UAVs in the routing path in one period to calculate the packet loss rate. Or flow path module calculates the initial path for each flow through follow table messages, which are the flow entries of each flow. And all the analysis information is sent to the statistics module, and then analysis results are forwarded to the monitor display module. The load balancing algorithm here selected from strategies will run in load balancing algorithm module, and updated path information is sent to the UAVs by algorithm distribution module through a packet out messages. And here you can see a picture which is a flow chart, and in this figure it shows the calculation processes. For example, the path for flow 1 is A, B, D, E, and then G, and A1, D1, K1, J1 is equal to 1, which indicates that flow 1 passes through these links. And there is a dictionary here. The dictionary for flow 1 is AB equal to A1, AC equal to 0, BD equal to D1, and so forth. And this is the dictionary for network topology. And this figure shows the flowcharts of the load balancing algorithm in SDN controller. The controller monitors network and evaluates the link state by the network variance and flow load. When controller detects the number of times exceed the counter threshold, it collects communication devices information of the overloaded link, including priority of devices, the IP addresses. Then they take advantage of digester algorithm and to calculate the optimal path and the weight. If when the optimal path obtained, they check the power of the UAVs, and if the power consumption exceeds the power threshold, UAV and links, it connects to are removed from the topology and replan the routing path in a new topology. When the optimal path is determined, a device with highest priority is switched first according to the priority of devices. The link load state will be detected again after a switch over. This slide provides the summary of 3 papers. The problem that addressed in the first paper was how to control UAV networks in an automated and scalable fashion in distributed environments. And they provided a novel SDN framework called SwarmControl, includes control framework and drone programmable protocol stack for self-optimizing drone networks. It was a distributed manner and the multiple UAVs are used. The drone PPS is implemented in Python. The second paper, addresses how to handle mobility at the edge and manage resource challenged in untethered and reliable UAV-based LTE networks. They proposed an edge EPC solution that they call it a SkyCore that can reliably and scalably support a multi-UAV LTE network deployment. And it is implemented in C++ and P4. And the last one was how to manage and utilize the massive information and maintain a topology of UAV network. They provided a monitoring platform in a SDN controller, and they also provided a load balancing algorithm for UAV network. It was a distributed matter and multiple UAVs are used, and it implemented in Mininet Wi-Fi. And there are the references. I hope you enjoy.